Okay, this is a talk about Apache Spark. My name is Petar Zečević. I'm coming from SV Group company in Zagreb. I'm also organizing Apache Spark Zagreb meetup group. We have monthly meetups. We've got interesting presentations talking about machine learning and things like that. The next meetup is on March the 9th. If you're interested, please come. It's in Preradovićeva street in Mama Club. And I'm also writing the book Spark in Action by Manning. If you're also interested, I've got a discount code for 39% off on the book. It's on the last slide. So if you're interested, wait for the next last slide. So what I'll be talking about is a gentle introduction to Spark and the context around Spark and why would you use it. So what is Spark? Why to use Spark at all? How does it work? And what can you do with it? Then you'll have a couple of minutes, hopefully, for questions, if any. First, let's see among you, please show your hands. If I've never used Spark, I mostly barely heard about it. Okay, that's what I expected. So this is the talk for you. I played around with it on my laptop or something. All right. Okay. I'm using it, or I'm planning to use it in production, maybe. Oh, all right. Okay. So what is Apache Spark? It is there's a big packed definition. It is a distributed, general purpose, large scale data processing engine. So let's unpack this definition a bit. So distributed obviously means it runs on many machines, which we normally call a cluster. And computations, it parallelizes computations. If you write the program, it is running in parallel on those all those machines in the cluster. It sends program to data, not the other way around, like, for example, SETI at home program, which sent data to your, if you ran it on your laptop, you could help SETI, right, find the extraterrestrial life. They would send you a piece of data, your laptop would crunch it, and then would return the result to the central server. This works in the opposite way, because data is actually potentially huge. So Spark works like Hadoop. It serializes program, sends it to your machine in the cluster, and that machine works on the data it has access to. It is a general purpose, so it works across industries. You can use it for any task you like. You can read any kind of data, write any kind of data, practically, and does whatever Java, Python, R, and Scala can do. Except it doesn't have access to GUI or anything like that. It is large scale. Obviously, it's got. We think about large scale. That's big data. And we immediately think of social network companies like Facebook, LinkedIn, Twitter. And it is really big data. For example, Facebook grew at a rate of about 8 users per second. And LinkedIn like 6 and Twitter 2, I think. So that's a huge rate of growth. And all those users are not just standing idle, they're sending messages, uploading videos and stuff. And obviously it's not just social networks, it's banking, healthcare, biology, physics, weather, astrophysics, some simulations and stuff. You can, in your own organization, maybe you've got enough data to employ some big data framework like Spark. But you should have enough data, which means that actually, if your data fits inside one relational database or one machine, it doesn't have to be. It can be pretty faster to process it on one machine than to use a distributed system, because there's an overhead of serialization and managing of cluster machines and stuff. It is obviously a data processing engine. It's about processing data. It's not about It's not an ERP system, it's not a web framework, it's about processing data. So why should we use Spark instead of, let's say, Hadoop MapReduce, or generally? Well, Spark is first of all fast. That's its main selling point. It runs mostly in memory, keeps data mostly in memory. Unlike Hadoop, who stores it mostly on disk HDFS. It is therefore especially fast for iterative tasks that need to reuse the same data every time. It can be 100 times faster than MapReduce in memory and 10 times as faster than MapReduce on disk. And in fact, it broke a sorting world record in 2014. That's a Daytona sorting benchmark, which was held previously by Hadoop. And Spark sorted 100 terabytes of data in 24 minutes with 200 machines, and it took Hadoop something like several hours with 2,000 machines. So that's a pretty, good improvement. And recently, Project Tungsten in version 1.5 brought additional optimizations with it stores data outside of Java heap, so garbage collection is not used for collecting that data. It's Spark manages it directly, and the data is also binary encoded in, so it's not using the default Spark Java serialization for the data. The API itself is very consistent and simple, concise and simple. It's actually functional programming. I guess most of you played around with Scala, Python, so it should be familiar to most of you. And now in Java 8, Lambdas. So functional programming itself is much more expressive way to program these things. And distributed collections, you operate on distributed collections, and you use the same, more or less the same functions as you would use on the local collection. So it's kind of familiar. It's a very powerful concept because you working on distributed data and easily. It's got APIs in Scala, Java, Python, and R. And this is the example of simple and concise API. This is the MapReduce word count example in Hadoop MapReduce. It needs 3 classes: the main class for setting up the job and everything, the mapper and reducer, and it can also use the combiner class, the fourth class. And Spark sets up the job and does all of this in this small code. So it really is powerful and expressive. It is also a unifying platform because in one single framework you can use all those functions like batch processing, real-time processing, analytics. You can write SQL queries to query the data, machine learning and graph algorithms. This is the Lambda architecture. I don't know, I forgot the name, sorry, colleague talked about. So it's basically, you have, no, it was Davor from, okay. It's actually, you've got batch layer. This is normally how you would, you store data forever in a let's say, cloud, DFS file system or something. And you have some kind of computation, aggregation of that data, which produces some batch views. But this aggregation takes like an hour or 2 or 15 minutes, and you would like to see your results immediately. And you have new data coming all the time. So that's why Nathan Martz, who wrote a book about it, he was the first one to introduce this term, Lambda architecture, where he said actually that we can use another speed layer which is holding only temporary data and aggregates only temporary data, produces those temporary real-time views, and data queries would know how to combine the both so that you can see the real-time results. And you can use this Lambda architecture, you can use Spark for implementing both of these layers, and much in the very similar almost the same way. So it's the same API. And finally, Spark has gone mainstream. That's another reason to use it, because it's got real large community. It's been Apache Spark. It's one of the most busiest Apache projects. Used in many companies, like all those big companies are using it in all major Hadoop distributions, like Cloudera, Hortonworks, MapR, and IBM Big Insights. There are many packages and connectors developed for all the big data databases like Cassandra and HBase and all others. There are conferences, 3 world conferences, 2 in Americas, East, West Coast, and now in Europe, and there are also certifications for Spark. And IBM last year pledged to commit 3,000 developers solely to Spark, so that's kind of big news, and I expect to see, much to see from this initiative. So how do you use Spark? You install basically it on similarly to Hadoop, you install it on all those machines in your future cluster. You configure and start the cluster, then you write an application, then you submit it to the cluster, and then it executes there. But you can also use, you don't have to use the Spark cluster that comes with Spark. You can also use a Hadoop Yarn. Yarn is Hadoop's second generation MapReduce, which is open to other types of applications, not just MapReduce applications. So you can run Spark on top of Yarn, or you can run it on Mesos, which is also another general execution platform. And you can run Spark in Mesos in Docker containers, for example, which is kind of interesting. And you don't have to write application, a jar per se. You can use Spark shell, which is similar to Scala shell or Python shell. You can write your program as you are. You can see the results of your actions immediately. No need to compile it and submit it and stuff. And you can also write a web application which connects to a Spark cluster, and you can start your application that way. This is the basic architecture, kind of simplified picture. You've got this client JVM process, which contains the driver process, which actually runs your Spark application. It communicates with the cluster manager, which can be Spark cluster, Yarn, or Mesos, and it demands from cluster manager to start a certain number of executors, which can be running. Each executor can be running on one machine, or they can be on several of them on a single machine, and so on. It depends on the configuration of the cluster. And I've heard the largest cluster, I think, is something like 80,000 machines, Spark cluster in somewhere. The RDD is this is the part of how. RDD is the core notion in Spark. It represents a distributed collection. This is what I was talking about. It is a resilient distributed data set. So it's a distributed data which has certain transformations similar to local collection Scala or Python connections like map, reduce, filter, join other RDDs, and so on. And transformations create new RDDs, and actions execute RDDs and get results. So RDDs are actually lazy. They don't execute immediately, but wait for the first action, and then look at all of the actions performed on this RDD previously, and then Spark serializes this as a program and sends it to each of the executors, which then really execute the actions and then get results. So this is a quick example from this is word count in Spark, which is ubiquitous in it's always in each Spark presentation. There is at least one word count example. So this is mine. This line SC, that's a Spark context object, which is always present in Spark application. this line says it to read textual file from this path, and this already creates an RDD object, which represents elements of this RDD are lines from this file. Then we say do a flat map, which transforms each element to one or more other elements. This line says we will split these lines and actually create RDD which contains only words from this file. Then we map a word to a tuple which contains a word and the number 1, and then reduce by key, which does a shuffle among all those. It's called shuffle, which means that it matches all the different keys from all the executors and then shuffles them around and combines them together and executes this function on the results. So it basically adds all those ones in each word, and the result is the count RDD, which contains each element has a word and a count of how many times it appears in the file. And nothing gets executed here until we call this collect, which is an action, and that actually executes the RDD and pulls all the results to the driver process, which means you need to have enough memory for it to hold all the results. So this is very easy to do with Spark, and with other frameworks that would take that's actually a really complicated thing to do in a distributed system. So what can you do with Spark besides what I already shown you? These are the functional components in Spark and parts of its API. So you've got Spark Core, it contains most of what I already shown you previously. You've got Spark Streaming for getting real-time data, MLlib, which is for machine learning, SQL, and graphics. I'll go through them one by one. So Spark Core works with RDDs. You can load, save, parse raw data, like in example you've seen. You can transform, aggregate, join different data sets, communicate with the executors, and orchestrate the work. Then we have Spark SQL, which works with data frames. Data frames can be converted to RDDs and vice versa. They handle structured data, organized in column, much like the tables in the relational databases. And you can load and save structured data to external data sources like all kinds of databases like Hive and relational databases, Oracle, PostgreSQL, whatever. And you can use SQL commands. You take a data frame and you register it as a table. So Spark knows that data frame by a table name. So, and you can execute like select all, join, whatever. And you can start the JDBC server, which looks at those registered data frames, and you can point your JDBC application like Tableau for visualizations and nice graphs and whatever you like. And it talks to Spark and your Spark programs through JDBC. Spark Streaming handles real-time data. So it's coming over TCP/IP socket or from Kafka, Flume, or there are a bunch of connectors. And you use the same API as from the batch job. So you can build a machine learning model or use machine learning model to predict something based on the incoming data. But it's from the latency from half a second and up. So if you need something quicker than that, you would probably use Storm, but it's usually not necessary, and benefits are usually greater than latency. So Spark ML, as I said, it's got a bunch of machine learning algorithm implementations for doing classification, regression, clustering, PCA, TF, IDF, and neural networks are under development currently. They're not available yet. Spark Graphics organizes data in vertices and edges, and you have different graph algorithms. You can present, social networks in a graph, and or web pages, network of web pages, links between them, and then you can use PageRank, which was made by Larry Page from Google. That's where the page comes from, the name, which actually ranks pages according to their importance in the graph. Connected components, triangle count, shortest paths, and so on. If you would like to learn more, I invite you to come to our meetup. The next one is on March the 9th. And you can buy the book and use this code to get 39% off, if anyone's interested. And if you have any questions, so I think I'm a bit early, so yeah. Yeah. Yeah, so by default, Spark expects it to be on HDFS. Well, you can configure it to that default, but usually it's on HDFS or some distributed file system. So it uses Hadoop API to read the file, and each executor reads this API, and each executor gets a piece of data from that file. So it operates only on those lines that it received. It directly accesses the file. Any other questions? Yeah. Hazelcast. Hazelcast is in-memory distributed like key value store, right? Cache. So I don't think you can execute arbitrary programs in Hazelcast, right? You don't have streaming component, you don't have machine learning algorithms in Hazelcast. It's like you can use Hazelcast to store intermediate results, for example, and query them, which would be faster than storing them on HDFS. So, but it's much different than key value store. It's a computing engine, yeah? No, not in production. I know some installations. One of them, I know one that's in production in Croatia. They're using it for receiving log files and then aggregating log files and seeing in real time what their users are doing. Actually, I have a similar example in the book, which does really that. You can download it, and it's in Docker containers. It's easy to set it up and see it in action. Yeah.
You said Spark is kind of a natural progression from a large relational database.
Well, it's not for storing data. It's for loading data, computing, and it's computation framework. Database is for storage. So it's well, it doesn't depend on the way the data is stored. You can have your data stored in the way you have it stored right now, and Spark can access it. If Java can access it, you can access it from Spark. So, but it's not storage. The Spark is not for storage. It's for aggregating and processing. Yeah. Is that a question or scratching? Scratching. Okay. No other questions? Yeah.
Thank you.
Please come again.
We have a lot of time left, so either you go to coffee or ask more questions. So.
Yeah, sorry, I was, when I was rehearsing,
no
it was half an hour.
Yeah.
I kind of.
Oh, just.
Yeah, there's a Flink framework, which was made in Germany, I think, in a university in Germany, which is kind of cool, and it's a competition to Spark. Spark is mostly batch, and then it's streaming. Spark streaming is like mini batches, so it gets data from a stream and divides it into mini batches, and then does the same thing as with any data it loads, but only on this time frame time window, no. And the Flink does the opposite. It's actually streaming, and it can do batch with like it does streaming. It's streaming first, so it's kind of, and it's Project Tungsten was made, which I mentioned, which packs the data binary and everything. It was done to kind of, because of Flink, because Flink also manages data directly and packages it binary. So Spark was kind of lagging behind on the performance wise in comparison to Flink, but now they're much more or less the same. And Spark is, I think, more mainstream than Flink, so I don't think Flink is going to win, but you never know. Okay, thanks again.